Yeah, so I'm going to be talking about evolutionary algorithms which are driven by LLMs. So LLMs performing the mutation step, where you go from a parent to a child, which is normally a modification of the parent. And I'm going to talk about how important it is, or how helpful it is, to measure the diversity of your population and use that to steer the algorithm as it goes. I've got a couple of experiments showing that this seems to help, by contrast to extremes where you explore the search space quite radically, and another alternative where you exploit quite heavily the best solution that you found so far and encourage the LLM to search for small iterations on top of that. So I'm not going to talk about kernels here. I'm going to focus on evolution, in particular LLM-driven evolution. So first of all, what are evolutionary algorithms? So here's a very simple set of 5 steps, which characterizes the vast majority of evolutionary algorithms. So you start by initializing a population of candidate solutions to whatever problem it is that you're trying to solve. Now, this could be the optimization of a non-differentiable function. It could be some problem involving discrete inputs, which are hard for you to apply gradients to, or gradient descent to. Really, evolutionary algorithms are a pretty general purpose tool that let you solve any kind of optimization problem. So when you initialize, this could be a single draft solution that you've put together. It doesn't have to be a full population of radically different attempts. The initial population could be 1, and you can quickly expand that to the full population size that you're intending to have. But after initializing, you evaluate the fitness of each individual in your population. So for us, this might be measuring how well a program that's been written performs a certain task. So you give each of your individuals a fitness score, and then you hold on to the fittest, the top 3, say, or just the top 1, top 5, along with maybe a random mix of other worse performers, and then mutate them. So the mutation step in classical evolutionary algorithms, when it comes to, say, optimizing a function, you may just apply a random mutation, adding perhaps random noise to your inputs. And once you've done that, you start again, essentially. So you go back to evaluating the new population, hold on to the best, and mutate again. And you just repeat this again and again until either you hit a stopping criterion or you run out of compute. So the key trade-off that you're always facing with these algorithms is exploitation versus exploration. So exploitation, this is the idea of hanging on to what you know works well. So it might be the case that early in your loop, you find a pretty good looking solution, and you would exploit it by making sure it's never dropped from your population. So a maximally exploitative version of this algorithm would always hold on to the best solution that you've got so far. That's called elitism. And it's used across the board, elitism. You generally never drop your best performer, but you would maximally exploit it. So it would become the parent to all the new children in the next generation. So it's just maximally used for the mutations. And this means that you often struggle to find much diversity. It's a way to kind of constrain the creativity of the loop, or the ability of the loop to find interesting, like novel solutions that are too far of a jump from this best one that you happen to find early on. And on the other hand, you could explore too much, meaning that you allow too many of your candidate solutions so far to become parents that are mutated. You might have like a pretty mediocre result that you allow to produce children, and these children are probably also unlikely to be very good because they're jumping from a pretty low bar. And so these two things are sort of traded off against each other. And part of the trouble with designing these algorithms is finding the right balance between exploitation and exploration. And yeah. Now, diversity is one thing that you can control either through a run or, I guess through a run, you can either like adaptively tweak the amount of diversity that you're targeting. Now, that's what I'm going to propose here. Or in advance, you can say, throughout this run, I want the generations, the populations to have this fixed level of diversity, which you would just continue to target all the way through. Now, typically, it's helpful to do a lot of exploration early on, so try out a load of stuff early on, and then later in the process, once you've found some fairly good solutions, exploit them and try and take small steps from those already successful solutions to something slightly better. And to do this, it requires like having a dynamic method for controlling the exploration balance. We'll get into how you do that later. But first of all, here's a quick example of an evolutionary algorithm. Now, the problem here is optimizing or minimizing a non-differentiable function. So this function, in fact, it is differentiable, but it's got many local minima, as you can see. Each of the dark areas is a local minimum that gradient descent would likely get stuck in. Now, in this case, this evolutionary algorithm is being run with too little diversity. So it's not exploring enough, it's exploiting too much. We're only allowing the very best performers to be mutated, and we're forcing the mutations themselves to be quite tiny. And you can see we get stuck in this local minimum here rather than finding our way to the blue star, which is the global minimum that we're searching for. Now, on the other hand, we might have too much diversity in the algorithm. So this is a bit of an extreme case, but here we're always holding on to the best solution, which is called elitism, but we're picking a random subset of the others to include as parents for the next generation. And we're also encouraging the mutations to be very large. And as a result, you end up with this kind of random walk. And it's going to take ages for you to like happen to stumble across the best solution. Now, this one is supposed to be a sweet spot. So this algorithm here, it has a sort of, I guess, just right amount of mutation, a sort of middling range for the mutation size. And it's also adaptive. So the better the solution gets as you progress through the algorithm, the smaller the mutations you allow. And we can see in this particular example, it happened to find the global optimum a lot quicker than the other two. In fact, it found it. Now, this is a classic theoretical result about these algorithms. And it applies to the three that we just saw. So believe it or not, if you run each of those algorithms long enough, no matter how bad they are, how long it takes, they're guaranteed to eventually find the global optimum. And that's because they satisfy these three conditions. So the first one is elitism, and this is generally used in every single algorithm like this. And this just means you always hold on to the best solution you found so far. Second condition is this ergodic mutation, and this means that any solution is reachable from any other. Now, that was true in the previous example because we were applying Gaussian mutations to the points, to the parents to produce the children. And the Gaussian distribution spans the whole real number line. And so in theory, you can get from any solution to any other. It might just be extremely unlikely. And selection pressure, this is another pretty standard rule that's applied to most of these algorithms. So you just require that fitter solutions, so solutions with a higher fitness score, are more likely to survive than less fit solutions. So yeah, it's quite easy to find an optimal solution if you have infinite time to wait and infinite compute to spend. But what if you don't? I'm going to argue that diversity, controlling the diversity of your population as you go, is a really powerful lever you can use to influence how long it's going to take to get to the optimum. Now, here's one more theoretical result, the last one we're going to talk about. And it's very specific, unfortunately, to this one particular task called jump K, which it's a bit flipping task. And a fitness function rewards an individual for having as many ones as possible up to a certain point, at which point it starts punishing the solution for having that many ones. But if you get beyond a certain amount of ones where you're getting punished, all of a sudden you get a massive reward, which means that it's pretty hard to jump from a decent reward to a massive reward, because you have to get punished quite a lot along the way to get there. So this is a classic, just quite difficult task for these algorithms. And these three strategies are proven to have different expected times to optimum. And these are the scaling laws here. So max exploits, this is the obviously maximally exploitative algorithm. It only makes very tiny tweaks. And so the chance of it stumbling across this like all one solution is very unlikely. It would have to make K changes all at once. And so it scales polynomially. And max explore is even worse. It sort of searches around the search space almost at random. And so it has to stumble across the solution. So this is even longer in expectation to the maximum. But this adaptive solution has a much nicer scaling law. You've got this factor of K in the denominator here, which means in expectation, it should get to the optimum a bit quicker. But this is just, I'll clarify, this is just for this task. And it's quite hard to find theoretical results that apply across the board to these EAs, aside from the Rudolph result that we just saw. It's quite hard to do theory about these things. But we're going to take this result as a positive heuristic that encourages us to test out these adaptive methods outside of this one example. We're going to find that it works quite well. And yeah, I've got some specifics on the particular adaptive algorithm here, but I won't get into it. Now, what would it mean to do this adaptive version of EA in LLM-driven evolution? So first of all, what's LLM-driven evolution? All it is using an LLM as the mutation operator. And the things that we're evolving here, they're not solutions to some optimization problem. We're evolving programs. So we are solving an optimization problem, but the solution itself isn't numerical. It's a program which we can run and then assess its fitness. Now, this is a very popular approach now. There are tons of methods. AlphaEvolve, ShinkerEvolve, FunSearch is a bit of an older one, which use the LLM as a mutation operator. But none of them has a kind of measured diversity signal that they use to tweak the exploration curve or balance through the run. Instead, they kind of fix a config in advance. So FunSearch, it splits the population into different islands, so different kind of isolated chunks of the population which evolve in parallel. And it gets rid of the weakest ones, reseeds them with the best ones, and it keeps all of its approaches from collapsing into one. So it maintains diversity this way, but it doesn't do so dynamically. Similarly, AlphaEvolve, it has a sort of feature grid and islands which it uses to preserve diversity. But again, it's not a dynamic method. It doesn't measure the diversity as it goes and tweak and push the algorithm in one way or the other. And ShinkerEvolve, it's sort of the closest of the three to adaptive. It has an embedding matrix or an embedding method which it uses to compare the similarity of two different programs. But it uses a fixed filter, so it just uses this to throw out programs that are too similar to others. So it's adaptive in a way, but not in the way that we're thinking about here. Okay, and yeah, this is the goal. So we want to build a sort of analogy from this adaptive method that we saw work well in the optimization problem when the mutations themselves come from a language model. Now, this slide's a bit silly, to be honest, because it looks back at the way mutations were done for programs in the pre-LLM era. And these mutation methods just seem absurd now. So things like tweaking strings, swapping lines in the code, swapping subtrees, changing operators. And the point I'm making here is that none of these things work very well, largely because they usually break the code. And so it takes forever until you find an edit like this that will lead to functional code, never mind actually successful code. But LLMs are really the ideal mutation operator because the mutations, the tweaks they make to a program are generally meaningful. They understand the code, meaning that the programs they write will very likely compile and be able to run. They're also able to combine ideas from multiple parents at once. So they could say, this method had this clever technique to parallelize a certain part of the program. This other one figured that you could use a larger step size, say, and it might combine these ideas into one. And when it comes to diversity, LLMs are great because they give us a ton of different levers we can pull to increase or decrease the diversity. So the three I'm going to mention here and we're going to use later are, first of all, the prompt itself. So we can just explicitly tell it in the prompt, like, be more creative, try something that's a bit more out there, or we could tell it, just focus on tweaking what we have, find a small improvement. We can also change how many parents it sees, and after we calculate the reward, we can bake this into our fitness function. So we can use diversity to choose which programs are selected to be parents in the next generation. Okay. Now this slide, I'm going to explain how the mutations happen. They're quite simple. I've tried to keep it as stripped back as possible for the purposes of this talk. So each new child is produced by a headless Claude code agent, and all it sees is the task spec, so description of the task, the selected parent program, or there might be multiple programs, and a strategy-specific instruction. So this is the thing I mentioned before, where we tell it either go crazy, try something out there, or focus on conservative small edits. And I gave it no tool access, no project context, so it can't see anything outside the parents that it's provided with. And the program scored outside of the coding agent in a sandbox. And we use that score as the fitness. Now, how do we actually measure diversity? So this is really easy when the individuals themselves are, say, like numerical, like multivariate inputs to a function. You can use any kind of distance metric, Euclidean distance, whatever you like. But it's a bit harder with LLMs. What Shinkrabol did, I mentioned earlier, they use an embedding model and measure the cosine similarity of the embeddings of two different solutions. But for the purposes of this, I figured it made sense to use an LLM judge. I thought an LLM judge means that we don't need to rely on having a good embedding model. Why not just show the judge all of the programs you've got and tell it to output a similarity matrix according to a rubric that I've given it. So I told it to output 0 if two programs are very different, 10 if they're absolutely the same, and I gave descriptions for what the middling scores should correspond to as well. So we get a matrix output, a kind of upper triangular matrix. And from this, we can calculate the population diversity, first of all. So diversity is kind of the opposite of similarity. So diversity is just 10 minus the average similarity in this matrix. And then for a given individual, we can calculate its novelty compared to the others that you've got in the population. So this is just 10 minus the average similarity of that individual with all the others. And we're going to use these downstream. Cool. All right. So once we've actually, yeah. So this is how we adjust the diversity pressure, and it's related to the similarity score. So this is what we use the similarity matrix for. And the way I've been doing this, you can think of the diversity pressure. For now, in the abstract, I'll tell you how we use this thing later. But it's meant to be a measure of how much diversity we want to encourage in the next generation. And I define it with this kind of scary looking function, which is actually a lot simpler than it looks. So we start with PT, which is the current generation's diversity pressure. And then we tweak it with a small addition with a step size eta. And these terms in here are either 0 or 1. And the first one's 1 if the similarity, the average similarity, is greater than some threshold, meaning all of the programs on average are too similar. In this case, we would want to increase the diversity pressure. They're too similar, let's try and make them a bit more different. And the second term here combines two conditions. So it has the opposite case to the previous condition. So we need the similarity to be low, and also for the current champion, which is the best solution found so far, to not have increased, to not have improved in the given generation. So that's what this sort of not delta t means. It means in the current generation, step t, the champion hasn't improved. So this means we lower p if the similarity is too low and we haven't been improving. Cool. So this is the formula that I use to calculate the diversity pressure. But how do we use the diversity pressure? So I'm going to use it as inputs to a function that determines one of these three sort of tweaks or knobs that we can turn within the LLM or within the evolutionary algorithm. Now, the first one is how bold the prompt is. The second one is how much we reward novelty in the fitness function. And the third one is how many parent programs we show the agent. So I'll show you exactly how we plug the diversity pressure PET into a formula to tweak each of these. And in the experiments later, I'm testing each of these individually. So you can think of these as three different approaches to controlling the diversity within an evolutionary algorithm. So first of all, the prompt. So I've got three buckets here. So if this target diversity pressure P is small, we'll tell it make a small refinement or words to that effect. If it's in the middling range, we'll tell it make a moderate change. If it's large, we'll tell it make a bold structural rewrite. And empirically, we do find that these changes to the prompts have a material effect on the creativity of the LLM mutation. Now, this is very sort of coarse, three buckets, but I wanted to keep it simple for this presentation. Cool. Now, the second one, this is novelty. Specifically here, P controls how much we value novelty when we're choosing which individuals to hang on to for the next step in the algorithm. And it's very simple. Instead of calculating the score or the fitness of an individual purely on the basis of its fitness function, so how well it solves the task, we incorporate this extra term which adds the novelty score for that individual, weighted by P. So when P is larger, this novelty score is going to have more of an impact on the individuals that are selected to act as parents in the next generation. When P is 0, we're just left with the base case, so the score being equal to the fitness function. Okay, now finally, inspirations. So this is just how many parent programs the agent sees at once. And again, I've kind of bucketed this. So depends on P. The larger P is, the more diversity pressure we want to apply, the more parents we show it. So if P is 1, this is equal to 5, we'll show the LLM mutator 5 inspiration functions. Basically giving it more ideas, more things that it can recombine, maybe more inspiration, gets it thinking out of the box a little bit more, perhaps. And yeah. Okay, and then alongside these 3 sort of adaptive methods, we've got the 2 baselines. So these are the 2 extremes. So in practice, you probably, you wouldn't really pick either of these. They're just meant to show really the maximally exploitative and maximally explorative alternatives that we could use. But the max exploiter always hangs on to the best parent, always encourages tiny edits, and we have this greedy survival function where we give massive preference just to the methods that are working well so far. We don't include anything that's, that would be scored as particularly novel if it doesn't perform well. And then max explore, we do hold on to the best parent still. It's always elitist. But for the rest, we select the parents at random. We always encourage radical rewrites. And yeah. So as I said, both are elitist and both are technically guaranteed to land at the optimal solution eventually. But we'll see they both just take far too long. All right, so finally to the actual task that we're going to try and solve with these algorithms. Now, this first one I pulled from the AlphaEvolve paper. And the objective is to arrange 12 points in a fixed rectangular shape so that the smallest triangle formed by connecting 3 of the points is as large as possible. So you can see in this kind of seed, like randomly generated arrangement, the smallest triangle is tiny. Looks like a line. But after running evolution, this isn't the optimal, but after running evolution, this is the kind of thing that we end up with, where it's just a lot bigger. I think in this particular task, the absolute optimum is like 0.33, something like that. And this is what we found when we ran the 5 different algorithms. So you can see that max explore and max exploit kind of sealing out fairly early on. I ran only 5 generations here. They're all seeded from the same parent batch. And by contrast, all 3 of these sort of adaptive methods continue to progress through the 5 generations. In this case, tweaking the prompt had the largest impact. But I think there's a lot of noise in here. I haven't included error bars. But generally, the 3 of these tend to perform fairly similarly well, actually, and clearly better than the 2 baselines. Now, in addition to this,
Yeah, so just a question. So what exactly is the action space here? Is it like code which places the points?
Yeah, sorry, I should have been much clearer about that. They're told to write a function which, given the dimensions of the rectangle, runs and then outputs an allocation of the 12 points. So it takes in 2 dimensions, it outputs the locations of the 12 points.
Okay, got it.
And the tests, the metrics here are based on that single point, but in theory you could test, they're based on that single rectangle that I showed before. But you could also test over like a big range of different shapes. Now this white line is a method that I haven't mentioned yet. And the way this method works is loop through a bunch of different values of P. So fixed P. So we fix P in advance, where P is the diversity pressure. And we say, for example, I want P to always be 0.5 all the way through the generations. So the diversity pressure should always be 0.5, meaning that the prompts encourage moderate exploration. We always have, I think, 3 parents. So those conditions are always implied and held constant throughout the generation. Now I looped over a few different values of P, and based on those runs, pick the best one. Now the important thing is, for all of these runs, regardless of the value of P, it's fixed all the way through. It's not dynamic. But I wanted to see whether the best choice of P that is fixed would outperform these three dynamic versions. And it doesn't, which gives us some evidence that adapting this diversity pressure as you go is a good thing to do. Here, this is the population quality. So maybe I should have mentioned this previous graph. It shows the current best solution that's been found at each generation. So very often you find the best early on and you're not able to improve it. That's the case for max exploit here. But this is the actual population quality. So you always have a population of 10, and this is the average across those 10 at each generation. And you can see that the three adaptive methods, their averages climbed fairly consistently. Max exploit ceilings out pretty early, but max explore, as we might expect, it jumps around a ton. So you very often find really terrible solutions that drag down the average. But because you're running elitism, you're always hanging on to the best one that you found, even if it was a few generations ago. Here we can see that, yeah, it jumps around a lot. And this is the diversity metric through the generations for each of the methods. So for max exploit, as we might expect, because we're only hanging on to the best few from the earlier round, very quickly the diversity drops very low, and we're left with a population of very similar programs. Max explore, it's encouraged to always create very significant changes on top of whatever parent it's seen. And we also hang on to a random subset of the parents from the previous generation. And so the diversity remains quite high all the way through. Whereas with the three adaptive methods, you can see that the diversity gradually drops as we go. And this is because of the diversity, that pressure that we're putting on the algorithm based on how good the solution it's found is, and whether there's too much similarity or too much diversity between the individuals at that stage. All right, and then a second task. This one it's called online bin packing, and the inputs are these rectangles. So you're given just a list of heights for these rectangles, and the objective is for you to fit them in as few bins as possible. So you can see here with this one was from a heuristic. 20 bins are required to hold all of the different rectangles, but under this evolved method, it manages to squeeze them into 19. Now again, the objective here for the LLMs is to write a program which, given an arbitrary input set of set of rectangles, it allocates them into as few bins as possible. Yeah.
So on the initial population, is it just a bunch of 10 working programs, or are they not even working programs, or is it just like a blank canvas? How are you creating the individuals for the very first generation?
Yeah, so for the very first generation, I asked Claude to come up with a heuristic-based, a single heuristic-based implementation. And so I start with a population of 1.
Okay.
And that acts as the parent for all of the first generation. Cool. So actually, we end up seeing very similar methods. Here, lower is better. And we see that the three adaptive methods outperform the two sort of extreme edge case methods, which we would probably expect, but it's good to see. And in this case, the novelty sharing, so this was sorry, what was this one again? Novelty sharing? My mind's gone blank. Yeah, okay, yeah, this was integrating novelty into the fitness function. this one performed the best of the three, but I think over a large number of runs, there would be quite a lot of variation into which does the best. And again, when we add this additional method in where we calculate the optimal kind of fixed diversity, again, it doesn't do quite as well as the adaptive methods. Okay. And I say theory predicted this result. It kind of did. This theory is based on one specific task, which is very different to the tasks that we have here, and which doesn't use LLMs. But I guess we could say that this heuristic that people have kind of pulled from this one result on this one task, and have shown empirically sort of extends to tasks outside of that, also extends to LLM-based mutation tasks. So it's good to see. And in the paper I'm writing, I'm trying to formalize specifically why we might expect this to be the case. Are these the takeaways? I think the takeaways are quite clear. So let's just jump straight to questions, shall we? If you've got any. And thanks for listening. Yes.
So I'd be curious to see if you just ask Claude or like Codex to zero shot or the very best program it can for solving these problems, how would that compare against the best performing after all of the evolution steps? Did you try that out, or what are your opinions on that?
I think that's right. I think it would do very well. I haven't tried it actually. I find actually in general it's kind of hard to force Claude to one-shot stuff. It often tries to do loads of other things, but my guess would be that it would do very well. These results do kind of disguise that we're putting quite a lot of constraints on both of these naive methods, particularly the max exploit. We really tell it just make a small tweak, and of course, Claude, by default would probably make a large tweak if it thought it could find a big improvement. But really, this is just meant to show, I guess the important thing is that the adaptive method beats whatever the optimal fixed diversity that you might want to target as you go. And so we might expect for much harder problems that Claude wouldn't be able to one-shot. This would be like a more successful approach. Of course, these two tasks are quite simple for Claude. But yeah, maybe when it comes to kernels, it would have a much tougher job of one-shotting, and in which case we'd have like more confidence in these adaptive methods.
And for like the broader mutations, like what did a broad mutation mean? Like how many like lines of code would it add? And do you have any like rough estimates on that?
Yeah, I never like explicitly bounded how many changes it could make.
Okay.
I didn't put any controls, didn't have like an eval checking whether it was actually like following the instruction well.
Okay.
But empirically it would often, so for example with max explore, it would usually do a complete rewrite and go in a completely different direction, which was often broken or sometimes good, but it was like over-indexed on trying to be different from the parent. That makes sense.
Yeah.
And for max exploit, I did observe that it would often just tweak maybe a parameter input to the optimization function that was being written. But I didn't go through and check all of them. I didn't have an eval agent doing that.
Did you do any tests where you combine, because at the moment each of the three diverse things are separate, T1, T2, T and T3. Did you start to explore what happens if you mix that up, if you can, where the diversity is affecting multiple things?
Yeah, that's a good question. So I should have been more clear, really. This T1 method, it adjusts the prompt depending on the diversity pressure that you intend. But it fixes, for example, the number of parents at 1, and it fixes the novelty sharing at just the fitness function. So you can think of each one takes an adaptive approach to the listed method, but takes the baseline kind of implementation for the others. I did try having the adaptive pressure applied to all 3 of the knobs at the same time. I didn't include it in the presentation because I didn't want to like clog up the graphs, but it seems to follow a similar trajectory as the other 3. It doesn't do markedly better, as far as I can tell. But that's something I'm gonna run in the paper and write up.
And maybe a quick question. How does it behave like asymptotically? Because you mentioned that it follows, in theory, the same convergence law like the original evolution mechanism. But here you have only a limited history of the population. You mentioned you have only 10 elements of the population. What could prevent, why you cannot have behavior like it will retry the same idea again and again, like from these 10 elements of the population, it doesn't improve, then it regenerates ideas that already failed in the past, but it doesn't have memory of it. So it will try it and again and again and never fit. And so maybe the question is, what happens if you increase the number of generations a lot, actually?
Yeah, there's like very limited theory about the scaling laws of these types of curves. So in like a given run, how would you expect this trajectory to look like on average? That's just like really hard to theorize over outside of really simple tasks. But yeah, my sense is that because this Rudolph result holds and we do have elitism and the other conditions satisfied, if we were to run this for infinite time, they would all eventually land on the optimal solution. One condition that's important is that you can jump from any parent solution to the optimal solution with greater than 0 probability. And that's true purely from the fact that LLMs aren't deterministic. Maybe we can assume they aren't. And so there's always a non-zero chance that it could just happen to output the optimal program. Obviously, it's going to take a long time if you're just relying on that. But yeah.
Okay. Thank you.
Cool. I think that's all the questions. Nice. We can wrap it up there then. Thanks very much, guys.
Thank you.
Thanks a lot, Jack.
Thanks, Jack. Great
Let
job.
me just stop the recording. There we go.